Okay, so now I want to solve this second example for these complex Fourier transform solutions for this problem, so you get more familiar, uh, but for the way you can apply and use these integrals. Okay, so this problem is kind of an extension to the previous problem that we had, an extension to this 1D diffusion equation. So we also here now have, we are going to also add the advection term. Okay, so example, find the concentration of the following instantaneous tracer discharge. So we have a discharge of a tracer instantaneously, and we want to find the concentration of that as time evolves, and also in space. So in space and time. So let me draw the domain that we have. So I'm gonna choose just black. Okay, let me draw this. This is kind of the domain that we have. I'm gonna draw it 3D, three-dimensional. Okay. So this is kind of the domain we have. Okay. And then here we have the tracer release. It's released here. So we have this. No, I think I did it badly. Let me do it again. Okay. So this is like the tracer that is released. Okay, so this is gonna be x equals to 0, and then this axis represents x, goes to infinity, and then here, in addition to that, we have advection. Okay, so we have a fluid, for example, that is moving here with speed v. Okay, and then it's the tracer is released here, and then it's an instantaneous tracer discharge, meaning that we discharge, for example, an amount of that, like GPL, instantaneously. So I show it with I, which represents instantaneous. Okay, so this GPLI is released here at just one time, and then at just at this space at x equals to 0. Okay, so the question is, find the concentration of this instantaneous tracer discharge, and the equations that we have are these: partial c over partial t plus v. We have also now the advection term, v partial c over partial x minus the diffusion term, d partial square c over partial x square, equals to the source term. Just add a source term, which is GPL instantaneous. This is the amount of that release, and then I'm going to multiply it by delta, and I'm going to explain what is delta. This is delta function, if you don't know. Delta at x minus 0 means at x 0, and delta at t minus 0 means t at time 0. So this is released at x equals to 0 and time 0. This is valid for x between infinity and minus infinity. And the initial condition of this problem is Cx and 0 is 0. And the boundary conditions are C and partial c over partial x go to 0 as x goes to plus or minus infinity. Okay. So we don't have any concentration at the beginning, and then we just have a source term that is instantaneously releases that tracer at x equals to 0 and t equals to 0. And we also have this advection term, which is an extra term compared to the previous problem. So that's the only change we have now. Okay, so before moving to solving this question, I want to have a side note here about delta function. So for those who don't know, this is just a reminder. So delta is also known as Dirac delta function, is used to model an idealized point mass or charge. Okay. So let's look at it. So if you have x here, any variable, so the delta function looks like this. This is the delta function. So it's gonna be 0 everywhere, except at one point, which is going to be infinity. Okay, so it's going to be infinity here, but it's going to be 0 everywhere. Okay, so two properties of this, two fundamental properties of delta function. So the first one is, so if this is x, for example, and this is, for example, x equals to a, this is going to be delta x minus a. Okay, so one property is integral from minus infinity to infinity of delta x dx is 1. Okay, so when you take this integral, this is defined as this, when in the delta, the integral of that, the sum of that should be 0, 1. And the other one is when you multiply that by a function delta x minus a dx, this should give you fa, the function evaluated at a. So it just converts the whole integral when you multiply it by the function evaluated at this point at x equals to a. So these are two properties that we need to know about delta functions. Okay, so important properties. Okay, so now let's get back to our problem. So the answer. So we have this equation, and now we want to solve that based on the complex Fourier transform solutions that we found before. So the first thing I want to do first, this is a trick, we remove the advection term, we remove the advection term by change of variables to a characteristic coordinate. Okay, and what I mean by that is we let eta be x minus vt. Okay, and then this is gonna remove our advection term. And the reason for that, just physically, is assume that you are moving with this fluid with speed v. Okay, so you are moving with this fluid with speed v, and so you are moving, you are in the moving coordinate system. Okay, so when you are in the moving coordinate system, this means that you don't feel this v, you don't feel this velocity. You are in the characteristic, one of the characteristics, right, of this problem. So you don't feel this velocity, and so this is kind of removed, right? So you see that as a moving reference, right? So in a moving reference, you don't see this one. This term is going to go away, and then you only see this diffusion, right? So you might see this diffusion and also this temporal change, but the advection term is going to be removed. So let me just rewrite the equations now in the new coordinate system, or is the characteristic coordinate. So it's going to be partial c partial t minus d partial square c over partial eta square. So I have removed the minus v partial c over partial x by changing this variable, equals to GPL I delta eta minus 0 and delta t minus 0. So I changed x to eta, and this is kind of, let me just rewrite it down. Delta t minus 0. So this is kind of a point source. It's kind of a point source at eta, which is released at eta and t. And this is now the converted equation. So now let me, now that we have converted this equation to a form that we can simply use the previous solutions, we can use this solution that we had for a general form of this equation, which is shown here, right? And just substitute the solution, the answer. So G is going to be 0 here because, no, let me, yeah. Now let me rewrite the solution here and let's see what's going to happen. So we have, using Fourier transform solutions, we have c eta and t equals to the integral from 0 to t. So let's see here the integral. So okay, now the difference is this term is going to be 0 and we only have this term. So the reason is fx is 0 in our problem, right? So we don't have any initial condition. So the initial condition is 0. So this term is going to be removed and we only have gxt now. So we only have this second integral in this problem compared to the last one, which was different. So I'm going to write the solutions for that. So it's going to be integral of 0 and t of 1 over 2 square root of pi d t minus t prime, the integral of eta from minus infinity to infinity of GPLI, instantaneous source, delta eta prime minus 0, delta theta prime minus 0, e to the power minus eta prime square over 4 dt minus t prime d eta prime dt prime. Okay. So in order to evaluate this integral, what I'm going to do is I'm going to use the property of delta function here. So if you have a function that is multiplied by f, by delta at x minus a. So the answer of that is gonna be f at a. Okay, so I want to evaluate this function, this integral. So this integral, this is kind of now my fx, right? So this is my f eta prime, say, right? Similar to this one. So, and so I have this term here, delta eta prime minus 0. So this means that eta, the answer of this is gonna be GPL I delta theta prime t prime minus 0 times f evaluated at eta prime equals to 0, right? So this gives me, so use delta function property, integral from 0 to t of 1 over 2 square root of pi d t minus t prime GPL I e to the minus, instead of f, I'm going to write e to the minus. So eta prime is going to be 0, is going to be eta square over 4 d t minus t prime times delta t prime minus 0 at d times dt prime. So now the same thing here is going to happen because we also have another delta function here. And so now this is going to be my function again, f t prime, right? And so I'm going to evaluate this integral again. So this is going to give me 1, it's going to be ft prime evaluated at 0, right? At this. So it's going to give me 1 over, or let me write it this way, because GPL is a constant. I can just bring it out, GPLI over 2 square root of pi dt multiplied by e to the power minus eta square over 4 dt, right? So t prime should be 0. We evaluate that function at t prime equals to 0, and this is gonna be the final solution. But recall that eta was v minus x minus vt, right? So I can just write cx and t is GPLI over 2 square root of pi dt e to the power minus x minus vt square over 4 dt. And this is going to be my final solution for this problem. So let me do it like this. Okay, so this is gonna be my final solution for this problem, for this tracer gas release, instantaneous tracer gas release with this equation. Okay, so I just want to make one small remark about this. So a remark or note: the solution looks like the normal distribution. Okay, so what is the normal distribution? Let me add one more page. So the normal distribution is defined as 1 over sigma square root of 2 pi. This is from your statistics or probability course. E to the minus x minus mu square over 2 sigma square, right? And mu is your mean, and sigma square is the variance, right? So here in this problem, if you look at it, mu is vt, right? And sigma square is 2 dt. So in our problem, mu is vt, and sigma square is 2 dt. So it means that the mean and the variance of the solution, the concentration, is gonna increase in time, right? So let me just draw it so you have a better feeling of what does this mean. So if this is x equals to 0, okay, and we go a long time, I want to show it a long time, that how does this look like. So actually this is gonna be time equals to 0. So at time equals to 0, we have a delta function. Okay, so the delta function is gonna be something like this. It's going to infinity, and an instantaneous source is released at time 0. So as we go on and on, so this is gonna be look like this function, right? So it's like a normal distribution. So let's look at time equals to t0. So t1, for example. So first it's gonna be something like this. It's like a normal distribution, and mu, the mean of that is vt at 1, for example. This is if this is t1, okay? And then as you go on and on, this is gonna go down. So let's look at it here. So for example, here it's gonna be something like this, and here it's gonna be something like this. So both the variance and the mean are gonna increase. So here, for example, is mu at VT2, and here is mu at VT3. So both the variance and the mean is gonna increase in time. So this is how the diffusion and advection works, right? So as you see, the diffusion increases the variance. So diffusion, so this is an important process in both mechanics, solid and fluid mechanics, or even heat transfer. So diffusion increases the variance, right? Diffusion is D, right, in the general equation that we had. So this is the diffusion term, and this is the advection term. Okay, so as you see, the diffusion increases the variance, it smooths out your solution, and advection moves the tracer, right? Moves the tracer's concentration. So this advection moves, this move is going to move that in space, right? And the diffusion is going to just smooth it out. It's going to kind of, as you see, is going to increase this variance. Okay, so this is the effect of diffusion, just as a physical intuition for you to understand how does this work. So as time evolves, you have this delta function at time 0, and then this just goes to this, and then to this, and then to this. So it's kind of spreads out, and also moves in space. Okay, so the mu is also moving in space, the mean of that. So this was the physical intuition of this problem. So let me just wrap up what we learned in this lecture. So we started solving two examples. One 1D diffusion equation, where 1D diffusion equation where we had a fluid in a channel with V equals to 0 without any advection, and with some initial conditions. So we had some initial concentration or tracer, and then we wanted to see how it evolves in time. So we substitute back the solutions into the complex Fourier transform, the general solution that we found before here, and then we found the solution for that. So because we didn't have any source term or gx here, so this integral was 0 in the first example, and we only evaluated this integral based on the initial conditions. Okay, and this was we found it as a function of error function, which looks like something like this. Okay, so this is the error function. And in the second example, we solved the concentration of this instantaneous tracer discharge that was, we had a source term here, which suddenly discharged this tracer at x equals to 0 and at t equals to 0. Okay, so this was our equation, and the initial condition was set to 0. So the solution of that, in the solution, because we have the source term now, but the initial condition fx is 0, so this integral was 0. Okay, and we only had to evaluate this integral. And we evaluated that integral by two just two notes. The first one is the delta function. So we define the delta function. If you don't know, the delta function has these two fundamental properties. And the other thing is we remove the advection term by this change of variable to the characteristic coordinates. So we are in a moving reference frame where we also move with the fluid, and so this this v term, this advection term, is removed if you move with that reference frame. Okay, so the equations, the new equations in the new reference frame is converted to this equation, which we can now use our solution for the complex Fourier transforms, and then we just use that and use the properties of delta function to get to this solution. So this was the solution for this instantaneous tracer discharge. And if you look at it, this looks like a normal distribution. And this was the physical intuition of that the diffusion in general smoothes out, the diffusion term smoothes out your solution, while the advection term kind of moves that, or moves that in space. So it changes the mean of the concentration, and the diffusion just smoothes out that concentration field. Okay. So in the next lecture, I'm going to give a little bit more insights into these advection diffusion problems. And then after that, we will be done with the analytics part of the course. This complex Fourier transforms was the last part of the analytics that you need to know. And then after that, we are going to start the numerics part of the course, and finite difference and other kind of topics that we need to know to solve the partial differential equations numerically. Okay, thank you very much, everyone.